Moving along to Proposition 40, equal triangles, which are on equal bases and on the same side, are also in the same parallels. Let's check out the setup. Let ABC and CDE be equal triangles on equal bases BC and CE and on the same side. So let's draw this out. So it's going to be our first triangle, ABC, and this will be a second triangle. So this is going to be the triangle ABC, ABC, and the second triangle is going to be CDE. These triangles are given to be equal in the sense of equal area. These two sides, BC and CE, are given to be equal. And Euclid claims, or this text rather, claims that if AD be joined, then AD is going to be parallel to BE. So AD, the line through AD, is going to be parallel to BE. And we move on to prove this. He says, for if not, let AF be drawn through A parallel to BE, which we can do by Proposition 31. So what we're going to do is we're going to start at A. We're going to draw a line parallel to BE, so parallel to this line down here. Going to come over here. It's going to meet the triangle there at a point which he calls F. And let FE be joined. So we're going to join F and E. And then we're going to do a little bit of reasoning about this diagram. We're going to see that this is actually an absurd diagram. Therefore, the triangle ABC is equal to the triangle FCE, for they are on equal bases, BC and CE, and in the same parallels, BE and AF, which we proved is true by Proposition 38. BC is equal to CE, AF is parallel to BE, therefore, the triangle ABC is going to be equal to the triangle FCE. They're going to have the same area. Also recall that it was given that ABC, this triangle over here to the left, is equal to the triangle DCE, the big one over here. And from this, it follows that the triangle DCE over here is equal to the triangle FCE by common notion 1. And you can see why this is an absurd situation. The triangle FCE is contained by the triangle DCE. It can't be equal to it. Doesn't make any sense. This is impossible. Therefore, the supposition that led to this absurdity, namely that AF is not parallel to BE, is negated, and therefore AD must be parallel to BE. As he says, similarly, we can prove that neither is any other straight line except AD. Therefore, AD is parallel to BE, which is what we aim to prove. Now, because there is a little bit of doubt regarding when this proposition was added to the elements, let's also go through the case where the two triangles don't have bases which meet in a common point, namely C. And the proof is more or less the same, so I mean, you could end the video here and just write out yourself, but I don't care, we'll go through it. So we've got the first triangle right here, which we're going to suppose has equal area to the second one, and equal bases. So these are going to be the same. So here's, actually, let's call this B. We'll say this is BC, that's A. And we'll call this one DEF. So if BC is equal to EF, and BC is in the same line with respect to EF, and these two triangles have equal areas, then it's going to follow that AD is parallel to BF. And how do we prove this? Well, we just do the same maneuver. What we're going to do is start at A. We're going to draw a line parallel to BC. It's going to intersect the triangle here. We'll call this intersection G. We'll join G to F. Then we'll think about this a bit. Remember, we're going under the supposition that AD is not parallel to BF. So we have two triangles, ABC and GEF, with the same base and the same parallels, therefore those are equal. And it's given that ABC is equal to DEF, and from this it would follow that DEF is equal to GEF. So the greater would be equal to the lesser, which is impossible. Therefore, the supposition that AD is not parallel to BF is negated, and therefore it is parallel to BF.